Hi, I'm Biraj Prabhu and I'll be presenting our work on active domain adaptation via clustering uncertainty-weighted embeddings. This is joint work with Arjun Chandrasekaran, Kate Saenko, and Judy Hoffman. Adapting deep models to new domains is an important problem as it is impractical to label a large dataset for every deployment. Ideally, we would like to be able to efficiently adapt models trained in a labeled source domain to a related target domain with minimal labeling effort. This problem has been extensively studied in prior work as semi-supervised domain adaptation. However, most prior work in this area assumes labels for a random subset of target data, whereas in practice, all target instances are not equally informative. The problem of identifying informative instances for labeling has in turn been studied as active learning. In our work, we focus on the less studied problem of active learning under a domain shift called active domain adaptation. Concretely, the goal in active DA is to adapt a trained source model to a related target domain, given the ability to acquire labels for a fixed budget of target instances. Unlike traditional AL, which focuses on learning from scratch, active DA allows starting from a trained source model but requires operating under an additional domain shift. We find that the two most popular AL paradigms are less effective for active DA. Consider a toy two-class problem where the solid pink and hollow blue denote labeled source and unlabeled target instances respectively. Uncertainty sampling selects instances that are uncertain under the model. Under a domain shift, uncertainty is often miscalibrated and thus leads to selecting uninformative instances. On the other hand, diversity sampling selects instances that are representative of the unlabeled data distribution, but does not account for examples that are already well aligned across domains, leading to redundancy. We hypothesize that an optimal strategy for active DA would jointly optimize for both uncertainty and diversity. We now present such an active DA algorithm that leads to cost-effective domain alignment. Our primary contribution is a label acquisition strategy we call clustering uncertainty-weighted embeddings, or CLUE for short. CLUE selects for labeling target instances that are both uncertain under the model and diverse in feature space. Consider a similar toy problem as before with three classes. After source training, some target instances are already well aligned across domains. To identify informative instances and minimize redundancy, we first weight target instances by model uncertainty. Next, to ensure that selected instances are both representative of the entire target distribution and dissimilar within a batch, we perform clustering in this uncertainty-weighted embedding space and select nearest neighbors to cluster centroids as samples for labeling. We show that the CLUE objective can be approximated via weighted k-means in model feature space with weights set to model uncertainty measured by predictive entropy. We then acquire labels for the selected instances and proceed to the next step, where we update the model via semi-supervised DA, leveraging all available source and target data. In our experiments, we try multiple learning strategies. Finally, we repeat this process of acquisition and update until the labeling budget is exhausted. We present experiments for image classification on 6 shifts from the domain net, digits, and office benchmarks. Consider the clipart to sketch shift from domain net. We first start with the ResNet CNN trained on the source domain. We plot accuracy on the target test set against the number of instances acquired for labeling from the target train set. On this shift, we perform 10 rounds of active DA with a per round budget of 500 examples. We fix our adaptation strategy to a recently proposed semi-supervised DA method and compare CLUE against uncertainty sampling, diversity sampling, and hybrid baselines. The red line in the plot corresponds to our method. As seen, CLUE performs as well or better than competing methods across rounds. We find these gains to generalize even to more challenging shifts from the domain net benchmark, as well as on other benchmarks while using different model architectures. Next, we try to vary learning strategies and observe consistent gains even when fine-tuning from source and in combination with domain adversarial learning. Finally, we illustrate the behavior of different methods on the SVHN to MNIST shift. Shown here is a t-SNE visualization of logics for incorrect and correct model predictions, shown as opaque and partly transparent circles on the target domain, along with instances picked for labeling by different methods. We find that uncertainty sampling acquires informative but redundant samples. whereas diversity sampling picks diverse but often uninformative instances. Clue, however, is able to construct batches of instances that are both uncertain and diverse. Thank you for listening. For more details, please visit our project page.